Hello everyone and welcome to Euclid Book 1 Proposition 5. So this is going to be another proof proposition. So again, the drawing doesn't matter as much since the logical reasoning is really the thing, but a good drawing can help you. So this proposition is all about isosceles triangle. So I've drawn myself a decently big triangle here that is actually isosceles, as you can tell. And the big goal of the proposition, just to tell you now, is to prove that for an isosceles triangle, the angles at the base are equal. So this angle, in other words, is equal to this angle right here. And also that the angles below the base are equal. So if we extend this line down and this line down, then the angle right here will be equal to the angle right here is the other goal. Okay, that's what we're doing. Essentially, we're going to do a little construction first, then we're basically going to apply proposition 4, the side angle side proposition, multiple times to finish the proof. So here we go. Proposition 5, in isosceles triangles, the angles at the base are equal to one another, and if the equal straight lines be produced further, the angles under the base will be equal to one another. So the givens, let ABC be an isosceles triangle having the side AB equal to the side AC, that's what we have right here. And let the straight lines BD and CE be produced further in a straight line with AB and AC. So what that means here is we want to extend this out to some point D and extend this line out to some point E. It doesn't matter where they are. I'm going to go ahead and make my little infinite lines here. There. I do not know why it is doing that lately. There we go. And there. Okay. And then we want to mark some points. It doesn't matter where they are, but some point D a little bit further down here, and some point E a little bit further down here. There we go. Okay. And then Euclid says, I say that the angle ABC is equal to the angle ACB and the angle CBD to the angle BCE. In other words, Euclid says that this angle right here is equal to this angle right here, and that underneath, this angle right here is equal to this angle right here. Okay. To continue this construction, let a point F be taken at random on BD. Well, that's easy enough. Let a point F be taken at random on BD. There it is. And from AE the greater, let AG be cut off equal to AF the less. So in other words, we want to figure out what the point is over here such that the distance from A to F will be equal to the distance from A to G. Okay. And Euclid says we know that we can cut off a line equal to some other line by proposition 3, but it's actually easier in this case because all we need to do is draw a circle centered at A out to F there. There we go. And since these are both radii of the same circle, if we just mark this as G right here, then we will have successfully constructed such that AF is equal to AG just like we wanted. So then we're good. That's what we wanted in the first place. Okay, so then we're good. Alrighty. Oh yes, and finally, so let a point F be taken at random on BD. From AE the greater, let AG be cut off equal to AF the less. And then finally, let the straight lines FC and GB be joined. In other words, go ahead and connect F to C and G to B, and that will actually end the construction. There we go. So everything else from this point on is just reasoning, and I would just basically try to mark on here to help you out here the reasoning Euclid employs to prove that this angle equals this angle and this underneath angle equals this underneath angle. As I said, we're going to employ basically side angle side multiple times. So let me just read the first side angle side argument, and then I will mark it on here after I've read it. So Euclid says, then, since AF is equal to AG and AB to AC, the two sides FA and AC are equal to the two sides GA and AB respectively, and they contain a common angle, the angle FAG. Therefore, the base FC is equal to the base GB, and the triangle AFC is equal to the triangle AGB, and the remaining angles will be equal to the remaining angles respectively, namely those which the equal sides subtend, that is, the angle ACF to the angle ABG, and the angle AFC to the angle AGB. So what does that mean? So the two triangles Euclid is comparing here is this triangle right here is one of them, right here. This triangle right here is one of the triangles, okay? And the other triangle is this triangle right here, that one right there. There we go. And Euclid is saying correctly that these two triangles are equal by side angle side because, for one, they both share the same angle at the top, so they literally share the same angle, okay? And then this side is equal to this side, okay? And then, of course, also this side is equal to this side. Okay. So again, if you're thinking this triangle right here has this side equal to this side, and this triangle right here, and this triangle right here has this side equal to this side, and this triangle right here, and they share the same angle at the top. So by side angle side, this triangle is equal to this triangle, which means a couple things. It means the remaining side, the bases, are equal. So in other words, it means that FC is equal to BG. Okay, we've proven that. And it also means their angles are equal. So it means that this angle is equal to this angle. So we've proven that now. That's one of the angles in the triangle. And it also means, oh dear, sorry. It also means that this angle right here is equal to this angle right here, because those angles are also in the triangle. So none of those angles are actually the angle we want. We want the two angles we need to prove here. That's going to help us on the way. So that is the first side angle side argument from Euclid. Again, means that this angle is equal to this angle is the big thing, and kind of this big angle here is equal to this big angle here is the second part of the argument. Okay. And then he continues. And since the whole AF is equal to the whole AG, and in these, AB is equal to AC, the remainder BF is equal to the remainder CG. So if you didn't get that here, he's saying that since this equals this, and this equals this, then the little remaining parts, right, this little remaining part right here, will be equal to this little remaining part right here. So notice here, and this is the argument he's about to make, we were sort of constructing two more triangles that we know are the same. So this equals this. This has already been proven equal to this by our last side angle side argument. And, you know, this, of course, equals itself. So in other words, what Euclid is going to argue next is that this triangle right here, okay, that little guy right there, is equal to this triangle right here, again, by side angle side. So actually, you could, all three sides are the same. We don't have a side proof yet. But all three sides of both those triangles are the same. And we know, yeah, and we've proven that this angle here, sorry, we've proven already from the last one that this angle here is equal to this angle here, which will complete the side angle side proof. But just to read it from Euclid, he said, but FC was also proved equal to GB. In other words, we already know that this is equal to this. Okay. Therefore, the two sides FB and FC are equal to the two sides CG and GB respectively. So in other words, BF equals CG. So this equals this, which is correct. And FC equals GB. So this equals this, which is correct. Okay. And the angle BFC is equal to the angle CGB. So in other words, this angle is equal to this angle right here. Okay. While the base BC is common to both, while this is in both those little triangles. Therefore, the triangle BFC is equal to the triangle CGB. In other words, this little triangle here is equal to this little triangle here. Okay. There we go. And the remaining angles will be equal to the remaining angles respectively, namely those which the equal sides subtend. Therefore, the angle FBC is equal to the angle GCB. So FBC, which is this angle right here, is equal to GCB, which is this angle right here. And that is actually half the proof we wanted. So, yeah, sorry, I kind of drew that badly. But therefore, the angle FBC, which is this whole angle all the way up to this line, there we go, is equal to the angle GCB. So that is, so we've proven now that the angles below the base of the original isosceles triangle are equal. So that's sort of half the proof right there. Okay. And the angle BCF is equal to the angle CBG. So and the angle BCF, which is here. Oh, let me erase these. So and the angle BCF right here is equal to the angle CBG right here. So these little angles are also equal right there. Okay. So we've done nearly everything now. We just need to finally, we've proven that this angle is equal to this angle. We've proven that this angle is equal to this angle. We've proven that this angle is equal to this angle. We just need to finally, basically by subtraction argument, argue that this angle is equal to this angle. And that final subtraction argument is as follows. Accordingly, since the whole angle ABG was proved equal to the angle ACF, so in other words, since this angle right here, this whole thing right here, is equal to this thing right here, we proved that in our first side angle side proof. Okay. And in these, the angle CBG is equal to the angle BCF. So in those, the little part right here is equal to the little part right here. The remaining angle ABC is equal to the remaining angle ACB, which means this sort of ends the proof. This is equal to this. Did you get that? So this whole thing equals this whole thing, but this little thing equals this little thing. So the remainders, the base angle and the base angle, in other words, must be equal as well. Okay. There we go. So the remaining angle ABC is equal to the remaining angle ACB, as we just said, and they are at the base of the triangle ABC. Okay. But the angle FBC was also proved equal to the angle GCB. In other words, we already argued that the underneath angle here is equal to the other underneath angle here. Therefore, we're done. But the angle FBC was also proved equal to the angle GCB, and they are under the base. Therefore, etc. QED. We have proven successfully that for our original isosceles triangle right here, the two base angles are equal. This angle is equal to this angle, and the angles under the base are equal. This angle is equal to this angle as well. And there we go.